Yes. David, I guess you should be chair of the, because you're the only one, or David, Sabetta, or Ganji. Yeah, I think those are the ones who should be chair.
I can be chair, and I allow you to do the introduction.
Yes, I will. Yes, definitely plan
John,
on that.
can you record?
Oh yeah. No, yeah, good.
Or, I mean, maybe I can.
Okay, you. Oh, I got it. Right
Okay.
here. Yes.
Recording in progress.
Okay, welcome everyone. This is a big day for Corey. Yeah, it's been a pleasure working with Corey all these years. He's a brilliant student, very creative, loved puzzles and applied that kind of creativity, intelligence to astrophysics and building the code and solving problems and astrophysics problems and code development and 3D printing. And just, went off and that totally surprised me with 3D printing and all of his discoveries that he's made throughout the years here at Georgia Tech. We're all gonna miss him. But today, we're gonna hear about the culmination of his PhD work. And he'll be talking about from particles to prints, simulating cosmic dawn and the children of the first stars. So let's welcome Corey.
Woo! Great. Well, first off, thank you everyone for coming. It's really great to see so many friends and family here and have your support. So yeah, I'm Corey Brummel-Smith in the Center for Relativistic Astrophysics in the Computational Cosmology group, led by John Wise. And yeah, I'm going to tell you about my PhD work, building computational and observational tools to help us understand the early universe, the first stars and the first galaxies. So here's an outline for my talk. First, I'll give you a little introduction to star formation and the history of the universe. Then there's 4 parts. So in part 1, we'll talk about developing triggered star formation simulations from one of the first stars. Then in part 2, we'll develop code, show you code that I've developed using tracer particles that can track metals produced in supernovae in cosmological simulations. In part 3, we'll model high-redshift galaxies and compare these models with real observations from the new James Webb Space Telescope to predict properties of these galaxies. And in part 4, something interesting and fun is 3D printing some of the models from our simulations. So overall, the goals of this work is to get a better understanding of the early universe, particularly the metal enrichment of the first stars and the first galaxies. So before we get into all of it, there's some terminology we should go over. Astrophysics uses lots of acronyms, and these are words that I'll be saying a lot. So first is redshift, labeled lowercase z, which is basically a proxy for how distant an object is on cosmological scales. It's called redshift because as the universe expands, light gets stretched and shifted to redder, longer wavelengths. So if we look at a distant galaxy and we observe its light, redshifted light, then we can infer things like how distant the galaxy is and how long ago that light was emitted. Next is a dark matter halo, or just called a halo. This is a spherical collection of dark matter that really dominates the gravity in a galaxy. It kind of is the host for where galaxies form. Next is a parsec. This is a unit of distance. It's about 3 light years, or 2 times 10 to the 13 miles. So that's an enormous distance on human scales, but on cosmological scales, it's actually pretty small. Adaptive mesh refinement, or AMR, this is a technique that we use in our simulations to, on the fly, increase the resolution in the simulations in regions that need the most computational power. So this would be in high density regions where stars are forming. Next is the initial mass function, or IMF. This is a mass distribution, a probability distribution for the masses of the stars. So you can have different types of IMFs. Like a top-heavy one, for instance, would have a higher fraction of high-mass stars. So this describes the distribution of stars that we see. Next is metals, capital Z. This is different than the colloquial use. In astronomy, everything other than hydrogen and helium is a metal. Next is POP3 stars, or population 3 stars. These are the first stars to have ever formed. They're metal-free, and they were thought to be very massive, so potentially hundreds of times the mass of the sun. Next is population 2 stars, or POP2. These are metal-poor stars, some of which would be directly enriched from metals produced in the first stars. So metals are actually really important to understand for understanding the evolution of the universe and star formation. So this is an astronomer's periodic table. We have hydrogen, helium, and everything else. The universe, the primordial chemistry of the universe, when the universe began, was just hydrogen and helium. And literally everything we see around us, the air we breathe, the things that were, the plastic that these 3D prints were made of, everything, all other elements were made in stars, forged from nuclear reactions in their cores or supernova explosions when they die. Now, metals are important to understand because they have a strong effect on the thermodynamics of the gas. Radiative emission, so these metals will emit light that allows the gas to cool and condense to form stars and galaxies. Here's a history of the universe. On the left, we have the Big Bang, the very beginning. Then this long period of dark ages where there's no stars. And then around 100 to maybe 300 million years after the Big Bang is the formation of the first stars. And they're very massive, they're very hot, they burn up their fuel quick, and so they live short lives and then explode. And as a result, there's none left in the local universe around us today. So 13.8 billion years later, in the present day, we see these massive galaxies, lots of metal-enriched stars, but none of the first stars. They're all long gone. And even when we use our most powerful telescopes, looking deep into space as far back into time as we can, these first stars, the POP3 stars, are just too faint to observe with telescopes. So they're really difficult to study observationally. So we use numerical simulations to model them and try to look for signatures that they leave behind in the next generation of stars. So here's how star formation works. Initially, you just have a primordial cloud of gas. Molecular hydrogen cooling allows this gas to cool and collapse to form the first stars. As those stars live, they forge metals in their core, and when they explode, they disperse these metals throughout the halo, enriching it with that metal content. And tens of millions of years later, those metals will collapse into new clouds, metal-enriched clouds that form the second generation stars, enriched with the metals from the first stars. And this cycle continues, continually producing more metals, forming new stars, and more supernova. And so over time, the metallicity of the entire universe just increases as more stars form. Now, since we can't observe the POP3 stars with our telescopes, we try to infer their properties by looking at the metal content of what are called extremely metal poor stars that have a metallicity of about 1,000th the solar value. The lowest metallicity star we've ever observed was about 10 to the minus 5 solar. So by analyzing the chemical abundances of these EMP stars, extremely metal poor stars, we can try to infer the properties of the first stars. And we see these EMP stars in places like ultra-faint dwarf galaxies and the Milky Way halo. Now there's a problem. If we're trying to infer the properties of the first stars from the chemical content of this one, we don't know how many of these stars enriched this one. So was it one massive star with high metal yields or many smaller stars? And so that brings us to part one, which is triggered star formation from a population 3 star. So in 2020, a paper by Daniel Skinner, who's online, and John Wise, they showed that nearly all halos form multiple POP3 stars at once, which means there's this degeneracy of how many POP3 stars are enriching the future generation. And this makes it difficult to infer the properties of the POP2 stars based on the POP3 stars, POP3 stars based on the POP2 stars. Now, triggered star formation could be interesting because this could provide a direct connection between just a single POP3 star and its metal poor descendants. So what is triggered star formation? This is when a shock wave from a supernova, when a star explodes, compresses a nearby cloud of gas, it becomes unstable and collapses to form new stars. So we actually observed this happen kind of naturally, or almost happen naturally in one of the cosmological simulations we were analyzing. This is a simulation that was run with Enzo, this hydrodynamics astrophysics simulation code that we use. It uses adaptive mesh refinement, and it has incredible resolution, 22 levels of refinement, where each level increases the resolution by a factor of 2. So we can zoom in all the way down to a minimum cell size of 4 AU, and this is a 42 kiloparsec box. So this is incredible resolution. So we zoom in and we see this supernova remnant and this cloud inside that wasn't destroyed by the supernova. And we can zoom in really far and see that this cloud is actually collapsing. It's cooling and collapsing to higher densities. And if we were able to run this long enough, it would have formed stars. Unfortunately, there was a problem with the simulation. We had to rerun it. After fixing the bug, this is what it looked like, and we saw some different results. So this is going to be a movie showing the density, the metallicity, temperature, and this quantity called the divergence of the momentum, which basically blue shows gas that's expanding, red shows gas that's moving inwards. And so here's the movie. There's the supernova. We see this metal-enriched gas washing over the external medium, starting to filter into the cloud. It's heating up the external environment a lot. But notice the cloud isn't really collapsing. The supernova didn't have a strong effect on it. It didn't compress it. It's not collapsing to form new stars. Now, if we fast forward about 1 million years, this hot gas that's cooling because of the high metallicity is accreting onto the cloud. The cloud is growing to much higher masses, but it's not collapsing to higher density. So triggered star formation didn't happen here. But how close was it to actually collapsing? That's something we can try to measure. There are two quantities called the James mass and the Bonner-Ebert mass that are very similar. These are thresholds for gravitational instability. So if you have a uniform cloud, which admittedly we don't, but we can do an approximation, spherical cow type stuff, we can measure the mass of this cloud relative to the James mass. If it's larger than the James mass, then it should become gravitationally unstable and collapse. The Bonner-Ebert mass is very similar. It also takes into account the external pressure confining the cloud. So it kind of lowers this restraint a little bit, makes it a little easier for the cloud to collapse when you include that external pressure. So here's a plot, 650 kiloyears after the supernova, showing the mass enclosed in a sphere centered on the cloud as a function of radius, the size of that sphere. And if we look at the mass enclosed relative to the James mass in blue or relative to the Bonner-Ebert mass in orange, we see that it nearly exceeds the Bonner-Ebert mass. This black line is that critical threshold. So if it were to peak above this line, it could become gravitationally unstable. Now, unfortunately, as we've run it longer, it doesn't actually get above that line. If it did, it might collapse to form stars. Now, the question is, would those stars be metal enriched, or would this just form new POP3 stars? And to analyze that, we can look at the metallicity along a ray from the tail of the cloud out through the core and out to where the star used to be. So looking at the metallicity along that ray, we see at 4 different times in the simulation, it starts at a very low metallicity, around 10 to the minus 7, the solar value, drops low in the core, and then rockets up to high values outside in the external medium. Then 300 kiloyears later, in the red line, the tail reaches high metallicity, but the part that's most likely to collapse to form stars, the highest density region in the core, still has a very low metallicity, around 10 to the minus 5. So this actually, if stars did form, these would be classified as extremely metal poor stars. Now there is one caveat. This is a lower resolution simulation. When we ran a higher resolution one, this metallicity in the core was even lower. So the metal enrichment wasn't very efficient in this case. Now that's just one case of where we thought triggered star formation might happen. Just because it didn't in this cosmological simulation doesn't mean that it's impossible in general in the high-redshift universe. So we developed idealized triggered star formation simulations to try to figure out what conditions would allow this to happen in a metal-free cloud applicable to the high-redshift universe. So other authors have done these types of simulations before and successfully produced triggered star formation. But they always used a solar metallicity gas, so it's not really applicable to the high-redshift universe. And what we do differently is we include a radiating star particle, so that we allow this star to radiate its entire lifetime before exploding in a supernova. And so we run multiple simulations with different initial conditions. Here are the free parameters we can vary in our simulation and a diagram of the setup. So we have this spherical cloud with this density profile that falls off to the external medium. It has a certain radius. It's at a certain distance from the POP3 star. That POP3 star has a certain mass that we can vary. That mass determines the explosion energy of the supernova. And then we can vary the density and temperature of the cloud, as well as the density and temperature of the external medium. So choosing some initial conditions, here's an example of one of these simulations. At first you're going to see, this is a video, you'll see this hot bubble that blows up. This actually isn't the supernova. This is the radiation from the newborn star. And so this shock wave from this radiation comes, it compresses the gas, it blows off the outer atmosphere. There's the supernova. And basically we see that the combination of the radiating star and the supernova just destroys the cloud. So these weren't the right initial conditions. So let's look at some different initial conditions. The cloud is a bit different here. This is just a uniform cloud that's kind of been smoothed on the outside. And we see the radiation washing over, the shock wave passing into the cloud. It compresses it significantly, is blowing off a lot of mass, pushing the cloud away from the star. And then there's the supernova, and again, this supernova just basically destroys the cloud. And a lot of the reason here is because the cloud was so affected by the radiation pressure from the star as the star was radiating. So we ran multiple simulations. These are some of the main ones. We ran actually a bunch of others that either didn't work or failed, but here's some of the main ones that we ran. Varying lots of parameters like the mass of the star, the temperature and density, the distance, the radius of the star, the supernova energy. None of these produced triggered star formation. So next we did a kind of a control study where we didn't allow the star to radiate. We just triggered the supernova immediately at the initial conditions as soon as the simulation starts. And furthermore, we looked up we found in the literature some analytical constraints on the density and temperature and radius of the cloud that supposedly would allow for triggered star formation based on these analytical constraints. And so here we just explode the supernova immediately. The shock wave propagates into the cloud, compressing it. That's good, but it wasn't the right conditions again to form stars. So we thought the analytical constraints based on the literature should have worked. They didn't here. So there could be either something wrong with the simulation or something just that we're not understanding about the processes going on here, maybe related to the cooling. We noticed that the speed of the supernova remnant was slower than we expected. It was barely supersonic with a Mach number of 1.5 in the cloud. And so more research needs to be done to really explore this parameter space more fully to determine which conditions would allow for triggered star formation and if this can happen in the early universe. Because ultimately, if we can get this to happen, it could provide a direct connection between a POP3 star and its metal core descendants. But yeah, in summary, we've developed these simulations. Unfortunately, we weren't able to get them to actually trigger star formation, but these lay the groundwork for more research into this question. But this brings us to the next part, which is another way of studying the metal enrichment of the second stars. So this is using what are called tracer particles. These colored stars, this is kind of just a cartoon qualitative diagram to help explain what these particles do. So these colored stars in green, pink, and blue, these are representing POP3 stars. Then these yellow ones, these are representing POP2 stars enriched with the metals from these guys. And with these tracer particles, we inject these tracer particles into supernova when these POP3 stars explode, and then these tracer particles will follow the gas, follow the metals into the sites where these new stars are forming. So we can look at these tracer particles around these stars and tell exactly which POP3 stars are enriching the POP2 stars. Furthermore, we can tell the fraction of metals coming from each one. So this could really help solve this degeneracy of not knowing how many stars are enriching the POP2 stars. So these are called Monte Carlo tracer particles, or MCTPs. This idea was originally developed by Shai Geno in 2013, and he implemented them in the Arepo code. And so we do actually a similar thing, and by implementing them in Enzo, which is the simulation code that we use. So when you think of a particle, it has like a position and a mass and a velocity to move around. But Monte Carlo tracer particles are different. They're a property of the cell. So you can think of them existing as at the center of the cell, but really each cell in the simulation just contains a list of particles, and that the way that they're advected from one cell to another or the way that they're moved from one cell, from cell I to cell J, is based on the mass flux of the mass leaving through I through the cell wall into cell J. And so the probability is given by the mass leaving cell I into cell J divided by the mass of cell I. And these are randomly sampled. So there's a certain chance that it can move and a certain chance that it won't. There's a higher chance it moves if there's a high mass flux. And so you repeat this process for all of the cells. and each time step. And so ultimately the particles are designed to follow the gas. Now there's a ton to talk about the development of these particles and the details of that, and making them efficient and parallelizing them and everything, but I don't have time for that, so I'm just going to tell you about the results and how these particles work. So this is a turbulence test. This will be a movie. This is basically, we just have a uniform box of gas where a driving force mixes it up to form turbulence. And on the left is the gas density, and then on the right is the Monte Carlo tracer density. And if the particles work, these should look very similar. So here's the gas density, Monte Carlo tracer density. It looks very similar on large scales. Now, of course, you'll immediately notice that it's grainy on small scales. This is this noisy data. This is actually expected, well understood, and not much of a problem necessarily. You can smooth these data with a small Gaussian smoothing kernel, and then you get a nearly perfect recreation of the density field. Furthermore, you can increase the accuracy of the particles by just increasing the number of particles you're using per cell. So this blue line, this shows the density distribution, like a probability distribution. The blue line shows the gas density, kind of a true value. And then these dotted, dashed, and solid green lines are approaching the gas density as we increase the number of particles. So that's one way to increase the accuracy of the particles. Now, the most interesting simulation that we've run is a cosmological simulation that includes star formation and supernova feedback, where each time there's a supernova event, we inject these tracer particles into every cell that the supernova is affecting. And those particles will then go on to track the metals that are produced in that supernova. This is a fairly low resolution simulation. There's 128 cells per side on the grid. It has a box length of 32 megaparsecs, so this is a pretty big cosmological simulation. And additionally, we include one Monte Carlo tracer particle in every cell in the initial conditions to track the density of the gas. So we have particles for the supernova and particles to track the density, the regular gas. So this is a movie of the simulation. This is the initial condition at redshift around 60 or so. And this is showing gas density. On this side is the gray particles. So initially these are uniformly distributed. And then we'll see red particles that form as supernova are produced. So you can see a couple things. The grayscale, the gray particles, they show the same kind of cosmic web structure as the gas density, as they should. They're forming these big clusters where halos are forming. And these red particles are ejected from supernova as they should be, as we designed them to. So they are doing what they're supposed to be doing, but are they actually tracking the metals? This is showing the gas metallicity, so a high metallicity in yellow and 0 or low metallicity in blue. And on the right is the same plot, but with the Monte Carlo tracer particles overplotted in red. And we see immediately that they cover all of the yellow regions just like they should. We see a lot of particles in the high metallicity regions. There's no particles out in the voids of low metallicity. Now the only thing is they don't completely fill out all of the high metallicity region. This is likely due to the low resolution of the simulation. There's a known thing that happens in these types of simulations at low resolution called numerical diffusion, where these fluid fields like the metallicity and the gas will spread out over time just due to the nature of how these calculations are done. So this may not be too much of a problem, but they do a pretty good job at following the metallicity. Now I think one of the most interesting things with these tracer particles is to be able to identify exactly where these particles came from, the star that formed them. So we tag each particle with the ID of the star particle that created them, and this way we can track which metals came from which star. Oh, this is a video. So we can zoom around. So in gray is the gas density, and then all of these colored particles they're colored by the supernova ID. So each color represents particles that came from a different supernova. So there are over 900 particles, or 900 supernova, 900 star particles in this simulation, with about 2 million Monte Carlo tracer particles. And so we can zoom into these clusters of where there are lots of stars forming, and we can see all these different particles from different supernovae and tell exactly which stars they came from. So this was really going to allow us to track the evolution of the metallicity from the top 3 stars to the top 2 stars. So in summary, I developed these Monte Carlo tracer particles in Enzo. They accurately follow the gas, they track the metals, and we can identify exactly where they came from, just as intended. So what needs to be done in the future, now that we've developed these, is they can be used to answer these scientific questions that we are actually interested in. Now, I was mainly focused on just developing these particles to build this tool that others can use, but now these can be used to run high-resolution cosmological simulations, just like the ones I showed you, but at much higher resolution. And then we can answer these questions of determining the exact number of progenitors that are enriching the top 3 or the top 2 stars. And ultimately, these particles will help us understand the chemical evolution of the early universe and hopefully aid in observational predictions to predict the properties of the first stars. Now, that brings us to the third part of the talk, which is modeling high-redshift galaxies and comparing our models with observations from the James Webb Space Telescope, this guy here. And so this is work that was published in the monthly notices of the Royal Astronomical Society that was done in my research group, primarily by Danielle and myself and Snigdha. And yeah, so let's talk about this. What is the goal of this work? Well, we want to try to determine properties of these galaxies that are observed by JWST, like the ones in these images. So these are this is called the James Webb Deep Field. These are some of the oldest galaxies, some of the first galaxies to have ever formed, just like the ones that we analyze in this work. So we want to try to determine properties of these galaxies, like the halo mass, the stellar mass, whether or not these galaxies have supermassive black holes in them, if these are active galaxies, if they have an active galactic nucleus, where accretion of matter onto the black hole glows incredibly bright and actually can outshine the galaxy in the rest of the galaxy and the stars in some cases, and determine if there's any contributions from the luminosity to the luminosity from high mass stars like POP3 stars or X-ray binary stars. Those are the things that we try to do. So why do we want to do this? Well, as soon as JWST released its first round of data, groups like Harikane et al. And Adams et al. 2022, they started analyzing these images. So these up on the top here are 7 different images at different wavelengths, so basically different colored images. They're black and white here, but these are basically different infrared images taken by JWST. And from the brightness of those images, you can plot that on a brightness versus wavelength diagram. So this is called magnitude, where smaller numbers are brighter, weirdly, and versus the wavelength, so the energy of the light. And based on the brightness of these images, you can get a single point on this diagram, on this graph. So you get 7 different points from the 7 images. And then what they do is they fit a stellar spectrum, so the distribution of light from the stars as a function of wavelength. They fit the stellar spectrum, this blue line, to these 7 data points. And so from 7 images, you can fit a stellar spectrum and determine things like the stellar mass in the galaxy and the star formation rate and other properties of the galaxy. Specifically, its redshift, how far away it is. And they were seeing much higher stellar masses and star formation rates, these brighter galaxies than we were expecting based on our current understanding of early galaxy formation. So the question is there something new to be learned there about physics? Do we not understand how galaxies form in the early universe? Or is there something wrong with the detector? Or is there something wrong with how they're analyzing these data? We thought maybe there's something wrong with how they're analyzing these data. And that's because they're assuming that all of the light in these images is coming from the stars. Now, the stars aren't the only luminous sources in the universe. If these galaxies have an active galactic nucleus, AGN, or if there's a top-heavy IMF that has a higher fraction of high-mass stars, if these galaxies have POP3 stars in them, or X-ray binaries, these are all things that aren't taken into account when they fit their stellar spectrum to these photometry. So that's what we do. We build a new galaxy spectrum model that includes all of those things, like a supermassive black hole, an AGN, a X-ray binaries. We test different initial mass functions, IMFs. And then we do the same process of fitting our spectra to the observations from James Webb, and we determine properties ourselves, like the stellar mass and the halo mass. So this is a diagram of how our model works, flowchart of the pipeline. So it starts with a star formation history. This is basically a model for how the halo grows over time and how it forms its stars, how quickly. From that star formation history model, we have two models that we can choose from. That gives us the mass of the stars, the age of the stars, and the metallicity, all the function of time. We feed those quantities into the stellar spectrum generator, where we can choose one of 3 IMFs, and whether or not it includes binary stars. And so that gives us the stellar spectrum, but we also calculate an AGN spectrum. So from the mass of the stars, we can choose these parameters that I'll explain in the next slide to generate an AGN spectrum. We combine the AGN spectrum and the stellar spectrum to get the SED, spectral energy distribution. It's another word for spectrum. For the whole galaxy, we apply some dust attenuation. We redshift it from its rest frame wavelength to the wavelength that is observed by JWST. We calculate how bright it is in each of the filters that JWST would observe this galaxy in. And then we vary all these blue parameters. These blue parameters are free parameters that we vary in our models. So these free parameters are the halo mass, the halo growth rate for one of the star formation history models, the AGN spectrum slope, delta BH, the black hole fraction, which is the mass of the black hole divided by the mass of the stars, and the optical depth in the visual band, tau t. This is basically absorption that occurs of the light from intervening gas between us and the galaxy. So these are all free parameters we vary in our models. So how this works is we choose some initial parameters. They don't have to give you a good spectrum that matches the data well. So here, this is showing the magnitude again, the brightness of the galaxy versus wavelength. The spectrum is shown in gray. And then the observations from JWST are the red points. And then our model magnitudes that we calculate from the spectrum are shown in the blue triangles. Now, this is a model that worked really well. This is once we found the right parameters, and our model matches the observations really well. But initially, when you start this process of trying to find the best parameters, it doesn't work like that. You just choose some random parameters. They don't have to fit well. They don't have to produce a good spectra. So you generate the spectra, compute these magnitudes, the blue triangles, and then you compute what's called chi-squared, which is basically a measure of how close your model is to the observations. So it's a sum over all the filters and the difference between your model magnitudes and the observed magnitudes, the difference between these 2 points for all of them. And then you take a step in this parameter space to a new place. So you vary the black hole mass, you vary the halo mass, you vary the optical depth. You take a new step into this parameter space and you ask, is chi-squared smaller than it was at the previous step? If it is, that means you're moving in the right direction. You're getting closer to a true value where your spectra could be the true spectra of the galaxy that matches the observations. And so basically you take this pseudo-random walk through this parameter space trying to minimize chi-squared and find the best fitting spectrum. Now, not only do you get the best fitting spectrum, the best parameters that are most likely to be the parameters for the galaxy, you get a whole distribution of them. So this is showing 400 different spectra with different values of chi-squared. The spectra are colored by chi-squared, and you can see that the yellow ones, they are near the observations. Those are low chi-squared, so they fit the data well. They fit the observations well, whereas like the blue and the green ones, these have a high chi-squared. These are models that don't fit the data well. So not only do you get this distribution of spectra, you get a whole distribution of these galaxy properties that, as you've been sampling around that parameter space. So distribution in halo mass, a distribution in stellar mass, not just the best value. It gives you more information. So there's a lot of results to talk about here, and I don't have time to go through everything. So I'm going to cover some of the kind of most important trends that we see in these data, in our results. So first off is some of the models fit very well, some of them didn't. Particularly the ones that used a top-heavy IMF and top 3 stars what are called the Yggdrasil models. These ones didn't fit nearly as well as any of the others. So for all the, another interesting fact is, so all these ones in blue, these are the different models. So this is using a different, A or B is the star formation history. The second part is an IMF, and then the third part is whether it's binary or single stars. All of these different models, regardless of those model choices, give you approximately the same chi-squared. Now they have different parameters, so this means that different parameters can fit those observations equally well. But that's not true with the Yggdrasil spectra. They have much higher chi-squared. They don't fit the data well. So why is that? This is likely most probably because the Yggdrasil spectra don't have this important feature that we see in these galaxies, which is this big jump from low magnitude to high magnitude, low brightness to high brightness. This is called the Balmer break. So in the observed wavelength, this has been redshifted. This occurs at around 4 microns in this galaxy. It happens around 360 nanometers in the rest frame when that light was emitted. But this Balmer break is caused by absorption of light by hydrogen atoms in stellar atmospheres. And basically, you need to have hydrogen atoms, the nucleus and the electron bound together to absorb these high energy photons and create this Balmer break. Now, the thing is, the Yggdrasil spectra that have a top-heavy IMF with high-mass stars that are hot and young and burning brightly, they are hot enough to ionize the atmosphere in the star. And so if you don't have hydrogen atoms, if you just have these nuclei and free electrons, there's no hydrogen atoms to absorb these photons that produce this Balmer break. So the Yggdrasil spectra don't have this Balmer break. If you try to fit the Yggdrasil spectrum, it might look something like this, and it'll just run through these points trying to minimize chi-squared, but you still have this large difference between the spectra and the observations on either side of the Balmer break. So ultimately, that's probably why the Yggdrasils don't fit very well. Now, interestingly, if we look at the stellar masses, this plot is showing the stellar mass we calculate for each of our models using the best fit parameters for each model. For each panel, so on the top is comparing with observations from Adams et al. 2022, and on the bottom is from Harikane et al. 2022. These horizontal black lines show the stellar mass that they predicted, and these letters show the stellar mass that we predict for each of our different models with labeled by these letters. So the models that use the normal spectra, the normal IMFs, A through E, we are pretty consistently seeing higher stellar masses than these other authors calculated. And so that's kind of counterintuitive and opposite to what we thought might happen. We thought by including these other luminous sources like AGNs and X-ray binaries, we might see lower stellar masses because some of that light from these images would be coming from these other sources. But we're actually seeing higher stellar masses. And unfortunately, this may be due to an oversight in how we built our model. We didn't include an important component, which is nebular continuum emission, where basically these hot ionized regions around young stars will emit a lot of light in the UV and the optical wavelengths. And if we did include this, it would have raised that flux, and some of that flux would be coming from this nebular emission, not from the stars, so we would see lower stellar masses. So unfortunately, this was just an oversight, and it was too computationally expensive and time-consuming to rerun all the models with nebular emission. Now, interestingly, with these other models, F and G, these are the ones with the top-heavy IMF and the Yggdrasil spectra that I talked about earlier. We are consistently seeing lower stellar masses, much lower stellar masses than the other models, and in a lot of cases lower than the other observations or the other calculations that these other authors have made. And the reason for this is, well, the AGN is dominating the spectrum. So the stellar component is very small compared to the AGN component. So does that mean that these galaxies actually have AGNs? Unfortunately, we can't say that with a high degree of confidence because, as we showed before, the Yggdrasil spectra don't fit the data well. They have much higher chi-squared. And so basically what's happening, since the Yggdrasil spectra, the stellar spectra, can't fit the data well, the black hole and the slope of the black hole, so the black hole mass, or black hole fraction, FBH, controls how bright the black hole spectrum is. Delta BH controls the slope of that spectrum. Basically, these parameters are free to vary as much as they want to try to fit the data when the Yggdrasil can't. And so the black hole is compensating for these, for the inadequacy of the Yggdrasil spectrum. But it's still not fitting the data well, and so it's unlikely that these actually have we can't say with confidence that these galaxies have black holes. So in conclusion, sometimes the spectrum was dominated by the AGN, but had high chi-squared. Most of the SCDs that we could fit well were dominated by the stellar spectrum. I didn't really show as much about that. Importantly, there were no significant differences between the different star formation history models, whether we include binary stars, or which IMF we used. In general, we were able to fit the data pretty well without, other than the Yggdrasil spectra, regardless of which of these different things we included. And importantly, we ended up predicting larger stellar masses than both of these authors. Okay, so that brings us to part 4, which is 3D printing all of these objects. And so these are all objects from astrophysical simulations. And I just think this is a really cool and fun, visually interesting way to show these objects. You know, as astrophysicists and astronomers, we're typically looking at our computer screens, looking at analyzing data on a screen in 2 dimensions. And to really bring these into 3-dimensional form, I think is really beautiful and adds a whole new dimension to how you can visualize these things. So to make these, you first need a simulation. You can run one yourself or download one from an existing repository of simulations. And then you need to locate a region of interest. So do you want to print the whole domain? If you want to make something like the cosmic web from a cosmological simulation, then you might use the whole domain. Or do you want to do a specific galaxy, like a subvolume within that domain? So if you want to print this supernova remnant, then you can select out just a certain region of the simulation. And there's a Python package called YT that makes this incredibly easy to do. You can cut out this region with just 2 lines of code, defining like a sphere where you want that sphere to be and how big it is. And then you need to decide what you want to try to print. And this really depends on what your goal is for what you want to visualize. There's lots of different fields in the simulation, like density and temperature, and you need to choose which of those fields you want to make what's called an isosurface, a surface of constant value, to make this contour that is the outline of the surface of these models. So if you want to do something like this that I did to make jets from an AGN, then you don't want to use something like the density, because the jets aren't really well defined in the density field. You could use the temperature if you chose the right value for the temperature, but overall it's just blobby, it might not come out as nice. But if you look at the radial velocity, these jets are fast-moving gas ejected from the core here. And so there's a sharp difference between inside the jet and outside the jet when you look at the radial velocity. So that would be a good field to contour. Now, to generate the surface, it's again very easy with YT. You can just call yt.surface. You give it that data source, like that sphere we made, then the field that you want to use, like density, and then the value of the density that you want to use. And then you can just export it as an OBJ file, which is a type of mesh file that you can read into your 3D printer or into a mesh editing software like Blender. So choosing the right value is really important. If we're making a galaxy like this, if you choose a density that is too small, you'll just get the outer regions of that galaxy. It'll be very blobby. If you choose a density that's too high, then you'll have some holes in there. You see these spiral arms, but it's very disconnected, be very difficult to print. But if you choose the right value, then you can still see the spiral structure. You have one solid model, and it's much easier to print and just looks better. Now, there are still these disconnected regions. When you generate that surface, it's not guaranteed to give you a nice closed surface that's all one piece. So you have to remove these isolated regions. And again, Blender makes this really easy. You can use this modifier called remesh, which will recalculate the mesh. And there's a little checkbox, remove disconnected, and it'll just automatically remove those for you. It's very, very simple. And so then you have a nice model that you can export and load into your 3D printer. So here's how we do that. Here's after exporting the model. cutting it and putting it on the bed. And so this is using a technique called FDM, or fused deposition modeling. Basically, this is a fancy way to say extruding melted plastic layer by layer to build up a model. And so this is an additive manufacturing process, unlike something like milling, where you take a drill and you remove material. This is an additive process where you're adding layers of plastic to build up the model. Now, here's a video. So this is loading it into the model into the 3D printing slicer software that basically generates the code that is needed for the printer to make the model. And so you can see the tool head here drawing out all of the lines in the first layer of this model. So like in orange, this is the outer walls. These green parts are really important. These are supports that aren't actually part of the model, but are needed to hold up floating regions that are like overhanging. So you always need a layer beneath the next layer to print on top of, to support it, to hold it up. And so parts of the galaxy, that are overhanging, if I was to print it here, I would need supports to hold up this area that's just over thin air. And so these green supports, these are just broken off afterwards, and I mean, it can be kind of time consuming to remove all of them, but ultimately they're not part of the model, they're just there to hold up the parts that need it. Now you have to think about how to cut and orient the model too. So if you just try to print one of these galaxies flat on the print bed on its face, it's gonna be a bad idea, because there's gonna be a very small amount of surface area in contact with the print bed. It's not gonna adhere to the print bed very well. There's a good chance that first layer will kind of peel off or get messed up. And furthermore, you'll need a lot of supports to hold up everything that's not touching the print bed. And it'd be pretty hard to remove such a large amount of supports on the bottom. But if you cut the model in half and turn them on their sides, put them vertically, then you have a large flat area to adhere to the print bed. The model's supporting itself in the center, so you don't need supports in those regions. And you'll actually get better surface quality because you have more layers that you're printing throughout the model, versus here you just have you have fewer layers. So you get better surface quality there when you orient it like that. So here's some images and videos of making these different models you see up here. So this is a spiral galaxy from illustrious TNG. This is this one here. I think it kind of looks like whipped cream or something. And there's a time lapse of my printer making it. And then here's a visualization of the gas density in this galaxy with a software called Nepari that is really useful for visualizing 3D data. This is a massive halo from the illustrious TNG simulations. These are cosmological, some of the most high resolution, most advanced cosmological simulations. So this halo has multiple galaxies in here, and kind of just looks like a big blob, but I think it's really interesting. So that was showing the gas density, now this is showing the temperature. This surface was made with the gas density. Then this is the supernova remnant from the triggered star formation simulation. Here's a bigger version of it in gold up front here. And so this one actually opens up, and you can see that cloud inside there, which is kind of cool. That was kind of hard to print with all the supports and everything. This is an interesting one. This is something called a jellyfish galaxy, which is basically when a spiral galaxy is traveling through the intergalactic medium at high speeds, the pressure from the gas as it's traveling through, it's basically like the galaxy's traveling through a wind tunnel, and it blows off these tails from the outer regions of the galaxies that makes it kind of look like a jellyfish. Here's a cool one. There's a big one of this over there. And here's this one. These are jets from an AGN from a simulation by Yuan Li in 2015 that I did some work on analyzing. But yeah, these are some AGN jets. This one here, this is a jet that encounters a dense wall of gas, so simulating the ICM, the intercluster medium. And so it's kind of like shooting a hose into like a pool of water or something, where you see these plumes coming up on the sides. That was run by John Zuhone. So in summary, yeah, it's just really cool to visualize astrophysical data in this way. That's truly 3D. And yeah, I just think it's really interesting to be able to see it like this in true 3D. Now there's some real benefits, I think, to 3D printing these data. And one, it can be used as a really engaging tool to stimulate interest in astronomy for scientific outreach and public engagement. Everyone who I've shown these to, especially kids, they find it really interesting, always asking lots of questions about it. And also, I think this can be really useful for visually impaired audiences who can't easily see plots and visualizations that we make, the movies that we make. But now with 3D printing, they can see these simulations and actually hold a galaxy in their hands. So I think that's really beautiful. So in summary, all of these 4 projects together, the goal is to provide a deeper understanding of the earliest stars and galaxies. So even though we weren't able to confirm a lot of our hypotheses and answer the scientific questions that we set out to with these simulations, we've really built the groundwork for fruitful investigation into these questions. So first with triggered star formation from a population 3 star, that might provide a direct connection between a pop 3 star and its metal core descendants. Then with Monte Carlo tracer particles, that will allow us to track exactly where these metals come from these stars and follow them into the sites of star formation of the 2nd generation stars. And then by modeling high-redshift galaxies in the early universe and comparing those models with observations. And finally, by printing all of the interesting and beautiful models that we make in our simulations. So that's pretty much it, and I'll take any questions.
Questions from the general audience, not committee members? Online, you can unmute if you have questions, or type in the chat if you can't.
Kind of a silly question. Why are some of the spectra named after the Nordic world trade from North?
Good question. I'm not totally sure. I know that the author, the person who generated this spectral template library for these pop 3 stars, is just really into Nordic mythology. I think there could be a kind of relation between, like, it's like the tree of life or something, right? And these pop 3 stars are the source of all metals, the first source of, like, I don't know, new metals, new life kind of thing, maybe.
Interesting, thanks.
So Corey, I have a question.
Yeah.
And one of the first slides you showed about the evolution of the universe, and this probably doesn't make sense astrophysically, but is there, you have the observatory over here.
Mm-hmm.
Where did the Big Bang start compared to where our galaxy is now? Can we establish that?
Yeah, so it's a kind of misunderstanding that the Big Bang happened at a certain point.
Mm.
The Big Bang happened everywhere. So at the early universe, everything just started expanding uniformly everywhere. So it's not like that, you and John are getting farther away from me. It's that you guys are getting farther away from me, but then you guys behind you are getting farther away from you at the same rate. So everything is expanding away from each other. So the Big Bang is happened everywhere. And everything is still expanding away from each other. So yeah, it didn't really happen at one point. There's not really like a center of the universe. There's either no center or everywhere's the center. Yep.
So based on human civilization history on our planet, what is the expected occurrence of these supernovas? Well, first of all, in our galaxy or in other galaxies?
So in the whole universe, they're happening all the time. In our galaxy, I don't know the exact rates. Maybe one every tens of years, hundreds of years. That's just an estimate if I were to guess off the top of my head. But
One a century.
one a century? Okay, so.
4 core plots.
Okay, well, cool. I had a good guess then. Yep.
it shows here birth of pop 3 stars and death of pop 3 stars. And we talk about how they're not super bright and all of that. And then later on when we're talking about James Webb, you were saying that, you know, the light from the pop 3 stars weren't really taken into account. So I'm wondering, like,
Yeah.
if they're not that bright, do they need to be taken into account? Or?
Good question. Yeah. So the light may, you know, the fact is there probably is light from pop 3 stars that is reaching Earth right now. It's just that it's too faint to resolve that star to be able to see its structure and the clouds around it or anything like that. So the light is coming in. It's, you know, non-zero. It has an effect. We can detect it in the detector probably, but we can't identify that that light is coming from a pop 3 star, because that pop 3 star would just look like, well, it wouldn't even look like a point of light. It would just be some additional flux that comes into the telescope. You
Like
wouldn't,
glare?
like what?
Like glare?
Not really like glare, but just some kind of unrecognizable light. Yeah. Background. I think that's a good word.
Yes. There's a question online.
Okay.
Did you develop the Monte Carlo tracer particles yourself? Are there any plans to run the Monte Carlo tracer simulations with supernova IDs?
So
Okay.
the idea of the Monte Carlo tracer particles was from Shai Genau in 2013, but he developed them for the Arepo code, which is totally different than Enzo. It's a very different type of code. It works in a very different way. So I got the idea from him, but I developed them myself for Enzo, which was a very different development process than it would have been for Arepo. And plans to run the simulations with supernova IDs. So we did run one simulation with supernova and IDs, but for the higher resolution ones, I don't know if I'll have time to run them. You know, I'm about to graduate, so that's probably going to be another group, another researcher that runs those simulations.
Emily.
Yeah, how many generations of pop 3 stars do you think there are?
I mean, kind of by definition, one. So as these pop 3 stars form, they create metals, and if those metals are sent out into the universe and enrich these clouds of gas, if those clouds of gas collapse to form stars, then they're kind of if they're metal enriched, they're by definition not pop 3 stars. So I wouldn't consider it a second generation star unless it's enriched, basically. So you could, but I mean, you could have the scenario that I was kind of talking about in triggered star formation, where the star would explode if metals don't enrich the cloud. Like if they can't mix in from that supernova remnant into the dense cloud, then it could collapse and form new pop 3 stars. Whether you would consider that a second generation star or a first generation star, I don't know, it's just a bit of terminology. I mean, it was the gravitational collapse may have been induced by the pop 3 star, but if it's not enriched by the pop 3 star, then I don't know, is that a second generation star or not? That's kind of just a bit of terminology, you know, I don't know.
So one more question. So as a non-physicist, it's hard to understand almost everything.
Fair.
But I'm just wondering, given the state of non-acceptance of science, whether these could be some way of crossing that bridge.
I hope so. Yeah. Yeah, I mean, I don't really know about the whole state of non-acceptance of astronomy and how prevalent that is. I haven't really encountered that in my work, because I'm mainly talking to people around here who are
there
doing
that
science.
you would encounter Big Bang.
Oh, true. Yeah.
Yep.
With young Earth creationists or something.
Yep.
I mean, yeah, I don't know if 3D printed models would help convince someone who thinks the world formed 6,000 years ago that the Big Bang happened, but I think maybe it might stimulate their interest into, I don't know. They'd probably just say that this is all fake, right? Like, it's just lines of code, just fake data, I don't know, fake images. I don't know.
I think if they were put in classrooms, that they could help the future.
Yes.
I have a silly question.
Yeah.
In your scientific opinion, do you consider Taylor Swift a pop 3 star? I had to.
I mean, she's got to have some like influences that really helped her form. So I don't know if you.
No, but why did they name them pop stars? I'm just curious. And I couldn't tell my brain like the whole time, but I was like, okay, who named it a pop star?
It's
Alright.
so it's short for population. So with population 1 stars are stars like the sun that are very metal enriched, and population 2 is like the second generation of stars that's less metal enriched. Population 3 is further less metal enrichment, so 0 metallicity.
That makes complete sense.
Yeah.
Well, it seems like it should be the other way around. The first stars are
Yeah.
population 1.
I agree.
Okay. So I think that's all the time we have for questions.
Okay.
Let's thank Corey again. We can take maybe 2 or 3 minutes because we have to finish by 5.